Okay, now in terms of continuing with the exercises from page 43, and another bit of a segue, and we have concerning integration. And now if we have the antiderivative of dy all over 2y minus 1, okay, this is one of the items where we have integration by substitution. And applying u substitution. So I have u is equal to 2y minus 1. And I have putting this in the context of differentials. So I have du is equal to 2 dy. And we have in turn putting dy in terms of du. So dy is going to be equal to 1/2 of du. So we're going to have, once again, say dy, we're going to have at 1/2 of du. And u is going to be in place of 2y minus 1. Okay, so I have the reciprocal of u upon dividing by 2y minus 1. And again, for dy, I have 1/2 of du. So we have 1/2 the integral of the reciprocal of u du. Antiderivative, we have 1/2 the natural logarithm of the absolute value of u, followed by the constant. And we have with the back substituting, we have 1/2 the natural logarithm of the absolute value of 2y minus 1, followed by the constant. All right, now, in what we have with regard to problem number 23, and we have in this particular setup, we have the derivative dy over dx plus 1 is equal to 2y. And we have imposed, okay, an initial condition whereupon y1 is equal to 1. And here I have the capacity to separate the variables. Okay, so if I isolate the derivative, first of all, we have dy over dx is equal to 2y minus 1. Okay. And here we can separate the variables by separating the differential and also dividing by the binomial 2y minus 1. So we have here, we have dy over 2y minus 1 is equal to dx. And here, once again, we can integrate over both sides. Okay. And once again, if you notice, we have from earlier, I start out with the antiderivative of the reciprocal of 2y minus 1. And again, so we have 1/2 the natural logarithm of the absolute value of 2y minus 1 is equal to x plus c. And if I just double both sides, so I have the natural logarithm of the absolute value of 2y minus 1 is equal to 2x. Okay, and just keep in mind, so we have 2x plus 2c, but again, constant times a constant is still going to end up as a constant. And so applying what we have now, again, I'm looking at solving in terms of y. And so once again, I can apply the natural logarithm of exponential base e. So I have e to the natural logarithm of the absolute value of 2y minus 1. We have is equal to e to the 2x plus c And e in natural logarithm will cancel out. So I'm down to the absolute value of 2y minus 1 is equal to e to the 2x times e to the c. And we have this bit of history to repeat. Again, a constant raised to a constant is still going to end up as a constant. All right, so I have the absolute value of 2y minus 1 is equal to c times e to the 2x. And we have, upon removing the absolute value indicators, okay, so we have 2y minus 1. So I'm going to have, strictly speaking, okay, so I have plus or minus c times e to the 2x. Again, whether it is positive or negative, okay, constant is still going to be a constant. So we have in the rewrite, so I have 2y minus 1 is equal to c times e to the 2 times x, and isolating the y term, so I have 2y is equal to c times e to the 2x minus 1. And we have, in the case of the general solution, and correction here, so I have 2y is equal to c times e to the 2x plus 1. And so we have, for this particular case, I have y is equal to 1/2 of c times e to the 2x plus 1/2. Okay, now you can keep the 1/2 at the front, but I just want to mention constant times a constant is still a constant. So you can write the general solution as y is equal to c times e to the 2x plus 1/2. All right, so in looking at what we have in the case of the specific solution, okay, that is going to satisfy what we have for y1 is equal to 1. So y is at 1 whenever x is at 1. So I have c times e to the 2 times 1, so I have ce to the second, and I have plus 1/2. And isolating c, so I'm going to have, taking away 1/2 from both sides, so I have 1/2 is equal to c times e to the second. And so taking what I have and putting in terms of c, so I'm going to divide both ends by e to the second, which will be the equivalent of multiplying by e to the negative 2. And so we have, in this particular case, all right, so we have, for c, we have 1/2 e to the negative 2. And we have, in the case of the rewrite, so c e to the 2x, we have 1/2 of e to the negative 2, and have times e to the 2x plus 1/2. And just condensing together. So I have e to the negative 2 times e to the 2x, and so we have multiplying together exponential base terms. So you have 1/2 of e to the negative 2 plus 2x from the product rule. So this is one way that we can display the result, or we could also say that we have y is equal to e to the negative 2x, make that negative 2 plus 2x, plus 1 all over 2. Now, in the case of what we have regarding number 34, and we have for this particular problem, okay, we're looking at working with exponential equations. Now, we have for the case in 34, okay, so we have with y is equal to c times e to the kt, okay, and we have with the initial conditions. Now we have y naught is equal to 1, and we have that y of 10 is equal to 6, and we're looking at what time t. Whenever y is equal to 2. Okay. All right, so we have, okay, just for the setup. Okay, so again, we have y is equal to c times e to the k times t. And we have with the initial condition. So we have y naught is equal to 1. And we have 1 is equal to c times e to the k times 0. E to the 0 is just going to be 1. So we have that c is equal to 1. And so we have with c at 1, we have in the rewrite, okay, now we have that y is equal to e raised to the kt. Now, for the next item and continuing, okay, now we will be looking at arriving at the value of k. So we have with the next condition, so we had that y of 10 is equal to 6. So y is at 6 whenever t is equal to 10. So we have that 6 is equal to e raised to the 10k. And in looking at solving for k, once again, I can just take the natural logarithm of both sides. Okay. So I have the natural logarithm of 6 is equal to natural logarithm of e to the 10k, and that's just going to go to 10k itself. And we have, now in looking at solving for k, okay, so k is going to be equal to 1/10 of the natural logarithm of 6. This will be the exact terms, and for approximating, now we have about 0.1791. And in looking at going from the general to the more specific, okay, and now that we had the value of k, all right, so we have, in this particular case, so plugging back in, so you have y is equal to e, and we have k times t, so we can just say 1/10 of the natural logarithm of 6 times t. And for what we have in this particular case, all right, so we have, in this one, so we have e to the t over 10 natural logarithm of 6, and we can say is equal to e to the natural logarithm of 6 to the t over 10. And so e and natural logarithm will cancel out. Okay, so we have 6 to the t over 10, or putting what we have in general terms. So this will be about e to the 0.1791 or 92 times t.